Hey everyone, thank you so much for joining us today. Uh, uh, Hello everyone, can you guys hear me? Can someone let me know through the live comment? Yeah, hi Usha. Yeah, I can. Am I audible? Uh, like, am I not audible right now? Okay, cool. So people are able to hear me. Thanks for letting me know. So I'll just get along with the presentation. Uh, So thank you so much for joining us. First of all, this is a collaboration between the Google Developers Group and the TensorFlow Group in Mysore. Hi everyone, my name is Samiran Roy. I'm the co-founder of a small data science startup called Tilde Hat. And today I'm going to talk to you about reinforcement learning. So I'll just jump right into it and show you some examples of RL in action. Okay, so starting with this. Yeah. So you notice over here, the reinforcement learning agent is trying to move the ball in such a way to hit one of these multicolored bricks. Okay. And you will notice that every time it breaks a brick, its score increases by 1. And the goal of the agent is to just hit all the bricks. So this is the agent in the beginning. It doesn't know what it's doing. It's just doing something randomly. So after 120 minutes of training, it plays reasonably well. So after 240 minutes of training, it starts doing something that we don't expect. Okay. Yeah. So the story behind So the story behind this is that there was this company called DeepMind, which Google acquired back in 2014 for some $500 million. Okay, DeepMind was working on an algorithm which would allow computers to learn how to play games just like a human being, just by watching a screen. Okay, and they ended up making one algorithm which was called DQN, which became very popular because it was one algorithm which beat human experts at more than 40 different games. Uh, in uh, using reinforcement learning. So they did this by uh, marrying two fields of AI at that time, which was gaining popularity. One was reinforcement learning, and another was deep learning. Okay. Next year, another breakthrough came in the form of an AI called AlphaGo. Okay. So AlphaGo is a reinforcement learning algorithm which plays the game of Go, which is just a board game like chess, and it managed to beat the world champion at that time. So Go is actually extremely a difficult domain for AI, because if you take the board of Go and you try to count how many different possible states can the board be in, you'll end up with 2 into 10 raised to the power 170. Okay, to put that into perspective, that's more than the number of atoms in the known universe. So if you want a computer to just record what is the best move to play at every state, that's not possible. We need some form of generalization. And one of the key comments that Lee Sedol made was that the AI played like an alien. So it used moves which no human has used before. Mainly because it was trained using something called self-play, where the AI was not playing against other humans, but it was improving by playing against itself. Okay. Uh, Even Elon Musk tweeted that this was a huge achievement, and experts were expecting this kind of AI to come into the picture 10 years from now. Okay. And I'll give you one last example of reinforcement learning in action. This was work done by the AI research lab at Berkeley. Uh, the idea is that you have a simulated robot on the screen and you show it any YouTube video. Okay. And you tell the robot that you have to learn the movement in the video. Okay. Initially, the robot will try something and won't be successful. But after a few hours of training, it manages to learn the movement on its own. And the cool thing about this is you can just give this robot show this robot any YouTube video, and you'll be able to, it will be able to mimic the movement. Okay. Okay. So I think I'll just check if everyone is with me. Okay, cool. So all of us are exposed to this current paradigm of artificial intelligence, which is deeply motivated by deep learning or supervised learning. Okay, where we have some kind of machine learning model which will learn what its input looks like. For example, in this case, our model will learn what an apple or a cupcake looks like. By learning, it will see a lot of training examples of apples and cupcakes, and later we can show this algorithm a picture of an unknown apple or a cupcake, and it will try to classify it into one of these two classes. So one of the things to notice is that this is something which is known as narrow AI. Okay. Uh, so basically it's AI which is really good at a specific task. Okay. So if you can either think of it as classifying images or recognizing speech or annotating, doing NER annotation on the data. But essentially what we have is artificial intelligence, which is really good at doing one kind of thing. And the second important point is that it needs a lot of supervised samples to be effective. It means that you need to give it lots of training data. Okay. So now, if we need to think about the next stage of AI, okay, what we need to do to solve tougher and tougher problems in AI, I'll just highlight some of the challenges that we face in AI. One is that of a large state and action space. So this was described when I told you the state space of Go. Basically, if we try to, there are, if you think of things like self-driving cars or uh, robots playing football or games like Go, uh, the amount of states of the game you can end up in is close to infinite. Okay, so there is no way to just record or just memorize what to do in every state. Okay, we need some form of generalization. Second is that we need to make AI which works well in a dynamic environment. So, like in Go, your opponent is constantly adapting his strategy to your own. So you will also have to keep changing your strategy in order to win against your opponent. Okay. Multi-agent cooperation. Uh, think of again agents playing football. You need to not just play well on your own, but you also need to communicate. You need to synergize with all of your teammates and collaborate if you want to really win and score. Temporal credit assignment is again a huge and very important problem in AI. It was introduced in the 1960s, okay, by Marvin Minsky. He's one of the founding fathers of AI. Uh, Temporal credit assignment basically asks the question that how good was an action? As simple as that. To put it into perspective, imagine the 2007 T20 World Cup, India versus Australia. Okay. So Australia was chasing down India's score and they were in a position where they were winning. Okay. And Dhoni at that time made a decision to give the ball to Sehwag for bowling. Okay. So at that point in time, we do not know whether that decision was good or bad. Okay. But later on, Sehwag managed to get a wicket and India managed to win. So later on, we can say that that action was actually good. But at that time, we are not really sure. So that is the problem of temporal credit. And finally, we have something called the exploration versus exploitation dilemma. Okay. So for an agent to like learn anything, it needs to make mistakes. Okay. So imagine that you're making a chess playing agent. It's performing really well. Okay. But the agent needs to deliberately make some mistakes sometimes so that it ends up in a hard to win situation. And then when he plays in that hard to win situation, it gains experience which is more valuable to it. Okay. So any kind of agent that you build is constantly in the dilemma saying that whether I should explore new things right now or I should just stick to what I know and win. Okay. So in order to solve harder problem statements in AI, we need to think about these challenges. Okay. And there are a few more challenges, but this is the crux of it. Reinforcement learning is a way to address all of these challenges simultaneously. Okay. So again, I'll check up whether everyone is with me right now. Cool. Huh. Yeah. So there are some domains, like there are many domains in which reinforcement learning is being currently used. It's not just theory anymore. Uh, I'm not going to cover all of this here, but I have a lot of resources which are present in this presentation, which you can look up to like get an idea of how RL is used in each of these fields. I'll just cover one. Okay. So the You all must be watching shows on Netflix. Okay. And for each show, Netflix shows you a caption. Okay. Netflix uses reinforcement learning to decide what kind of caption to show you. So, for example, if you take the movie Three Idiots, okay, different aspects of the movie might appeal to you and make you click on it. So, Three Idiots can be viewed by someone who is a fan of Amir Khan. Okay, it can also be viewed by someone who is a fan of love stories between Amir Khan, Kareena Kapoor, and it can also appeal to people who are who are reminiscing about their hostel life. So Netflix uses RL to kind of figure out, based on your clicks, what are your movie preferences and what kind of thumbnails to show you that will make you click on those movies. Okay. Okay. So very quickly, now I'll start actually talking about what reinforcement learning is. Okay. RL is a framework for making a sequence of decisions. Okay. So in RL, you have something called an agent, okay, which is residing in some environment. Okay. This agent can be a robot, or it can be a self-driving car, or it can be a bot that plays chess. Okay. The agent senses the state of the environment. It's just like humans, we are using our five senses to sense the environment around us. And based on this state of the environment, it does some thinking. Okay. And after it does this thinking, based on that, it takes an action. Okay. The key thing to know about this action is that it not only influences the state of the environment the agent is in, it also influences the future actions this agent might take. Okay. So many real problems have the same flavor. Imagine you're driving a car. So there you are constantly reacting to some dynamic environment. Uh, if you bump into someone, that definitely changes the state of the environment. Okay. Uh, if you make a mistake and go slightly off road, then you'll probably have to devote some actions in the future to get your car into the road. So we have this sense, think, and act cycle with us. So what do we do with it? We want this agent to learn some kind of task. Okay. And the way to do that through reinforcement learning is that you set a reward. Okay. You reward the agent for what you think is good behavior, and maybe you can penalize the agent for doing bad behavior, and the agent will figure out on itself actions that will maximize the reward. Okay. uh, think of how a baby learns how to walk. So it will get up, it will try something. Maybe it soars too much towards the left and it falls down. Okay. The pain from falling down will serve as negative reinforcement for the baby to not repeat that action again. Okay. And maybe if you have the baby's parents who are clapping and encouraging him to come forward, that will serve as positive reinforcement for the baby to learn how to walk. Yeah. So the most important takeaway from all of this is that you're not explicitly programming the agent, or you're not telling the agent what to do anything. You're setting some kind of arbitrary reward, and the agent is figuring out what is the best way to maximize that reward. Okay. So very quickly, small recap. Ah, so actually, there's a question that I would address. Netflix does fall into product recommendation. Okay. And what you say is true. So you can use normal collaborative filtering for any kind of product or caption recommendation. Okay. Where reinforcement learning comes in is to not make those recommendations stale anymore, in the sense that like you train some kind of model and it will tell you that this is the best product to recommend, or these are the best products to recommend, but you don't really have any mechanism from actually learning from or learning online from the user's feedback, uh, whether the recommendation, what your model told was the correct recommendation was good or not. That is number one. And second is that sometimes machine learning models are fully exploitative. They don't explore anymore. Okay. So if Netflix maybe wants to recommend you some really weird movie, okay, and it wants to learn from your feedback instantly, so there is where that is where reinforcement learning helps. So quick recap. Uh, if you had to build a reinforcement learning model to predict stock prices for you, okay, the most important part of formulating any problem as an RL problem is to decide what is the state, action, and reward. Okay. Uh, so the state here can simply be the raw history of stock prices that you observe. Okay. The action can be buy, sell, or hold by some amount. The reward could be just the profit you make on each trade. Okay. So now, very quickly, I'll cover some of the mathematics behind reinforcement learning. Okay. Formally, RL is modeled as something called a Markov decision process, or an MDP. An MDP consists of a set of states. So we have three states here, a set of actions which allow you to travel between the states. So over here, you can see the blue action, and you can see, so there are two actions. There's blue action and there is a red action. Okay. Uh, if you take S0, for instance, if you take the action red from S0, you will land up in state S1. Okay. If you take the blue action from S0, you'll either go back to state S0 or land in state S1. Okay. This is to model the stochasticity that happens in real life. Okay. You decide to overtake a traffic signal. Okay. You might be caught by the traffic police, you might get home safely. Okay, it all depends on a probability, and that probability is encoded by something called the transition probability function. It basically tells you what is the probability of landing in each state given an action. And finally, you have a reward associated with each state. Okay, so here, if you land up in state S0, you'll get a reward of 1. If you land up in state S2, you'll get a reward of -1. So this is all wonderful, but what do we do with it? Our goal is to find something called a policy. Okay. And policy is basically a mapping from states to actions. It basically says that if you're in this state, what is the action that you should take? Okay. And what kind of policy do we want to learn? We want to learn that policy which maximizes the rewards that we get. Okay. So for instance, if you take S2 over here, okay, if you take the blue action here with the probability of 1, you always go to S0 and get a reward of 1. Okay. With the if you take the red action, there is a high chance that you land up in the same state and you get a reward of -1. So a optimal policy should contain the blue action for the state S2. Okay. Some good news for you. An optimal policy, it has been proved that an optimal policy always exists if you formulate your problem as an MDP. Yeah. So this is how the environment in reinforcement learning is modeled. Okay. But the agent doesn't really have access to this kind of environment. Okay. So I have grayed it out. If you can see over here, all the agent knows right now, say that I am in state S1 right now. I have taken an action blue. Okay. The environment takes the state and action, simulates it internally, and returns the next state and the reward to the agent. So all the agent sees is something called experience, which is a tuple of 4 things. Agent sees the current state it's in, the action it has taken, the next state, and the reward. Okay. The goal of the agent is to figure out through trial and error, through connecting experience, some kind of optimal policy which maximizes its rewards. Okay. Yeah. So I'll just very quickly answer one question. The difference between reinforcement learning and unsupervised learning. Okay. So reinforcement learning has a time aspect to it. Okay. Whatever you're doing in reinforcement learning, every action you're taking is influencing the actions you will take in the future. Okay. Unsupervised learning is just taking a snapshot of the data and dividing it into different parts based on some kind of learning algorithm. So in unsupervised learning, there is no learning from feedback. Okay, there is no time or temporal aspect to it. The decisions you take don't have consequences in the future. Like for example, if you take the decision of studying computer science in your college, that will be an RL decision because it's going to influence the life, your life, which is coming after that. So back to the presentation. So what we need to do is this agent should learn some kind of optimal policy which should maximize the rewards. And there are several ways to do this. And I will very quickly cover one very basic algorithm, which is very popularly used. It's called QLearning. Okay. And you don't need to worry about this equation. All you need to worry about this is this QSA function. So QSA, or the action value function, takes the state and an action as input, and it will tell you the expected utility and goodness of being in that state S and taking that action A. Basically, it tells you that if you're in state S taking an action A, how good it is. Okay. Initially in QLearning, we initialize this randomly. Okay. So for our MDP, you can just fill in some random values initially. This table basically tells us that taking the blue action in any of the states is slightly better than the red action. Okay. So now what this agent will do is, suppose the agent is in state S0, it will, this is very important, it will consult this table to see which is the best action. Okay. So over here, the best action is blue. It will take that blue action. The environment will simulate that internally and tell the agent that you ended up back in state S0 and you got a reward of +1. So this agent collected some experience. Using this experience, we will update some kind of table. You just need to plug in values to some equation. And we'll end up with an updated estimate of how good it was to take the blue action from S0. Okay. So now, according to QLearning, it says that the action was slightly better than what we estimated. Okay, and which is true, because taking the blue action from S0 gets you back uh, to S0, and you got a reward of +1. So the QLearning algorithm believed that this was a good action. Okay, so if you continue to do this, okay, if you continue to collect experience and update this table, you'll end up with something like this. Okay, this updated table tells you that at state S0, blue action was the best, S1, red action was the best, and at S2, again, the blue action was the best. And basically what we have done is converge to the optimal policy. Okay, so by following this policy, we will maximize our rewards. Another piece of good news, QLearning always converges to the optimal policy, and this is subject to some small terms and conditions, and one of the important ones is to make sure that you explore from time to time. And by explore, I mean take the wrong action from time to time, so that the agent does not get stuck in a loop and manages to explore the entire MDP. Okay. So, okay, so there's a question from Akhil. How does the agent know the next state ST+1 unless action T is applied to the environment? So the answer is that the agent does not know what is the next state. Okay, the agent only knows its current state, and it knows what action to take. Okay, the environment takes those two things, simulates that internally, and tells the agent that now you have landed up in this state and you have got this reward. Okay, I'll try to demonstrate this in practice. Hopefully this works. Okay, so I hope this is visible. So this is a very basic game where you have to land a spaceship in the middle of these two flags. Okay, so at every point in time, okay, the environment is telling the agent what is this current state. So this current state is currently represented by this value of real numbers. Okay, and it will ask the agent, what action do you want to take? Okay, I'll just tell it, take the action 1. Okay, the environment took that action. Then the environment told the agent that this is the next state that you got, and you got a negative reward of this much. Okay, and this keeps happening in a loop. So I'm just going to put in some random values. So this is what is happening. Like in a good computer, it's millions of times per second, and the agent is learning how to play. Okay, so quick recap. We had our reinforcement learning agent, which was assumed to be modeled as something called a Markov decision process. Actually, not the agent, the environment was modeled as a Markov decision process. The reinforcement learning agent interacting with this environment does not know the model of the MDP. Its goal is to collect some experience and through trial and error figure out the optimal policy, which leads to more and more rewards. The way to do this is through an algorithm called QLearning, where you estimate something called the action value function. Okay, so there is a huge glaring problem with this kind of reinforcement learning formulation, uh, mainly because in the real world, in real problems, we don't have this very nice discrete states to work with. Okay, if you imagine a self-driving car, at any point in time, the state will be its raw sensor readings, which are floats most of the time. Okay, so the question is, how do you make reinforcement learning work with a continuous action space? Okay, and the idea is very simple. Represent this Q table as a neural network, or you can use any machine learning algorithm to represent it. Okay, and this is how the lookup would look like. Earlier, you were consulting a table to get the best action. Now we have this neural network or machine learning algorithm, which is accepting and say an array of floats, and it will output what the best action is. And there is ways to train this network so that it shows the same behavior as the table, which I'm not going to cover it, but I have left some references later. Okay. The great thing about using neural networks with reinforcement learning is that now you have the full power of deep learning architectures into your reinforcement learning. Okay, suppose you are doing reinforcement learning on images. So you know that there is this deep learning algorithm, deep learning architecture called CNN, which performs really well with images. So you can just plug that into your reinforcement learning solution. Similarly, you can do the same for sound and wavenet. So this marriage of neural networks with reinforcement learning is called deep reinforcement learning. It has been all of the three big highlights of RL that I showed you in the beginning, AlphaGo, Atari games, and the acrobatic robot. All of them used some form of deep reinforcement learning, and it's has been used to solve very complex problems. Okay, but it has some slight caveats. Uh, Normally, deep neural networks are hard to converge. Okay, deep neural networks with reinforcement learning are even harder to converge because the data distribution that you are training on is constantly changing. Okay, the training set is not fixed. The training set depends on where your agent is going. Okay, you need a lot of examples and you need a lot of expensive hardware, and there are a lot of small tricks that you need to do to get this network to converge. Okay, I'm not going to be covering them, but I have again links to them further in the presentation. Okay, so now coming to as a beginner, if you want to learn this field from scratch, uh, it's actually it's not very hard to do. Okay, it's a relatively new field. So what I would recommend you do is go through David Silver lectures. Okay, uh, there is this book called Introduction to Reinforcement Learning by Sutton Barto. You can refer to that. You can start playing around on something called OpenAI Gym. Very briefly show you what that is. If you want to try out some basic reinforcement learning algorithms, you can open Gym and you can select any of these algorithms that you want to try it on. And it will give you a very nice wrapper, which will actually look like this. This small loop of code is all you need to get started building your own algorithms. Okay. Apart from the lecture series, the book, and OpenAI Gym, those who want to do neural networks with use maybe TensorFlow neural networks with reinforcement learning, you can refer to this link. It describes everything from scratch, but I would recommend doing this only when you have done all the above. Uh, for people who want to go deep into this field, these are some resources that you absolutely must go through. Um these are some of the state-of-the-art algorithms that you must know. This DQN algorithm, which performed very well, came out 5 years ago. Okay, and there are a lot of improvements on that. I think the current best, and it depends from situation to situation, but the current best is something called random network distillation. You can look that up here in this link. Okay, RL is used in many different kinds of applications. Okay, how do you want to use RL in these applications? I've just listed out the applications and all the research papers which show you how they are used. So it's been used in robotics, it's been used in healthcare, used to train the AI for games. Uh, it's very huge for web layout, ad optimization from feedback. What kind of ads to show you? Like anything in which you are dynamically learning from user feedback, RL is very applicable there. Recommendation systems, Alibaba uses RL very extensively. Chatbots, real-time optimization problems. Google uses RL to optimize its power to its data centers, and by using RL, they got a savings of 40%. Intelligent tutoring systems, and even simulating some chemistry experiments. Okay, so now with some closing thoughts. So there is a huge engineering aspect to RL. Okay, so in the normal machine learning, deep learning paradigm, typically the majority of the people in the industry, what they do is they have a problem statement and they find some GitHub repo which solves that kind of machine learning problem. They transform their data to the form which fits that GitHub repo, and they have a machine learning solution. But the engineering aspect of RL is a bit more, because you have to decide what is the state, what is the action, what is the environment, what is the reward. Okay, and the learning of your algorithm heavily depends on what kind of decisions you make here. Okay, in many real life use cases like robots, self-driving cars, you don't start by just applying RL in a real world scenario. Like you don't just say that this is a car, let the agent drive. If it crashes, get a reward of -1. That won't work because the car has crashed. You can't do any more training. So in these cases, you use simulated environments. So you use simulations on your computer. So the advantage being you can do millions of simulations in a few minutes. Okay, and then use that information, transfer that into the real world, and then train your network. Okay, and last but the most important part of RL is that it's very unpredictable what you learn, what the agent learns. Okay, and I'll highlight that by giving two examples. So there was a competition back in college where were in control of a spaceship, and you had control of several spaceships, and you had to shoot all the other spaceships. We divided students into groups, um, teams of some groups, and found out who wanted what the best agent for the spaceship was. Okay, which team of spaceships was able to destroy all the other spaceships. So the team which ended up winning was not the ones which dodged bullets the best or fired bullets the best. The team which won, it did it by actually learning how to jam the communication channels between the robots so that the opponents are not able to communicate with each other. Okay, similarly, another example, so there was a project in my master's where uh, I had a team of 5 robots playing football. Actually it was uh, 2 robots against 3 robots, and the goal of the 3 robots was to keep the ball away from the 2 robots. Okay, and I thought that they would be dribbling and passing to each other, But in the end, they learned the policy that if instead of touching the ball, if you go and start beating up the other robots, they will fall down and they won't be able to reach the ball. So that is the policy they learned. So I'll end this project, this presentation, uh, with introducing Robocop. Okay, the official goal of Robocop is that by the middle of the 21st century, a team of fully autonomous humanoid robots should win a soccer game. It should follow the official rules of FIFA, and it should win against the winner of the most recent World Cup. So that is the goal they have set, uh, like 2150. I'll just close by showing you a small video of the robots that were in Robocop a few years ago.
Hasta la vista, baby.
Thank you, everyone. I have linked to the slides over here. So if there are any questions, I'll address them now. Okay, so I'll just go through them one to one. Any references for creating environment based on problem statement? So it's very dependent on like what kind of problem statements that you want to solve. There is no reference or no recipe to do it. Okay, you just need to be very sure about what you want to be in the state, action, and reward. Okay, so again, going back to the stock price example, it's an engineering problem. Okay, I told you that the state of a stock price prediction problem can just be the history of the stock prices. Okay, but you can also on top of that incorporate the news into your state by saying that I will do sentiment analysis on all the news articles which mention that stock, and I will add that into the state. Okay, you can also do some feature engineering on top of the stock values, saying that this was the relative strength index or this was the simple moving average of the stock. So in the end, it's an engineering problem. It comes from experience. Okay. DDPG3, deep deterministic policy gradient and temporal difference. So I do not know much about temporal difference 3. I don't even know if it's called temporal difference. DDPG I used back in the it was doing really well, and it was state of the art for I think 2016 or 2017. But currently there are algorithms which far surpass that, and DDPGs in general, it's very uh, it needs a lot of samples to train, so you need a very powerful machine. um, Face ID and facial recognition systems, I'm not aware if they use RL. Okay, but what you mentioned, uh, it's a valid point. They can definitely use some kind of reinforcement learning. Uh, However, the initial value is calculated in the QLearning network. So in the QLearning algorithm, you just set the initial values to random. Okay, then the agent will play. It will gain some experience, and then it will update those initial values. So you can start with anything, and the agent will converge to the optimal values. Okay, if there is anything else, you can let me know right now. uh, just wait for a couple of minutes. So okay, back to this simple so Vihan is saying that, okay, I'll address Vihan's point first. So you're saying that a simple recommendation model would serve the purpose and won't improve every time. Okay, yeah, okay, so this was not a question, it was a comment. How impactful is RL to real life? Yeah, we've seen computer impact real life. So yeah, in real life, it is actually it's very impactful. Okay, so computer vision, like any kind of machine learning or supervised learning, is a framework where you make isolated decisions. Those decisions are not affecting anything in the world. The moment where you want to do any kind of uh, you want to bring in any temporal aspect to it, like you're doing computer vision on cars, or a self-driving car, you'll need RL, because there you will need to make a sequence of decisions, and every decision is impacting your future decisions. um, Sandbox environments are actually very important for real life. I would encourage you to look up something called multi-armed bandits. They are very important. They are very extensively used in the industry, and very few people know about it. They are used anywhere where you want to show the user some kind of ad, or you want to do some kind of A/B testing. I would encourage you to look up, look that up. Okay. Since there are no more questions, you are always like you can reach out to me personally on LinkedIn for anything. Um, I think I have given my LinkedIn at the end of the slides. Thank you, everyone. Thank you so much for joining us. I'm ending this presentation right now.